Hello, this is HT Wingnut, and today we're going to talk about SMR hard drives and how they compare with conventional hard drives. I started testing SMR disks well over a year and a half ago as a personal curiosity experiment to see if SMR drives were a reasonable choice as a storage medium for Windows. It wasn't intended to be anything formal, just some basic benchmarking, but eventually just ballooned into testing SMR drives across multiple file systems like NTFS, ext4, ZFS, and XFS stored in various RAID, pooled, and single disk configurations using Windows, Open Media Vault, UnRAID, and even SnapRAID. File transfer performance, RAID rebuild time, and trim effects were evaluated and documented with results that I'll show later in this video. If you aren't aware, SMR stands for Shingled Magnetic Recording. This means the tracks in the platter that store the data are overlapped like shingles on a roof. CMR, or Conventional Magnetic Recording, store data on tracks with no overlap, and has been the traditional way hard drives have been constructed for the last 20 or so years, hence the name Conventional Magnetic Recording. But because of how SMR disks work, they're supposed to reduce the cost of hard drives because they can fit more data per platter than a conventional hard drive. So that way they can use fewer platters and fewer drive heads. But this comes with some caveats, namely write performance, which will be discussed shortly, and reason for these tests. Pretty much all consumer level hard drives sold today, and at least over the last several years, are disk managed SMR. So they're usually in the lower capacity of like 8 terabytes and smaller, whereas NAS and enterprise hard drives tend to continue to utilize the traditional CMR technology with capacities up to 22 terabyte currently. So the drives being tested, there's two sets of drives, 3 CMR and 3 SMR drives. You can see those drives shown here. The CMR are up here at the top, and SMR are down here at the bottom. Clearly there's no way to identify these drives as CMR or SMR from the outside. They look pretty much identical and basically function more or less identically except for the caveats we're going to talk about. In any case, I'm using these ST2000DM001 drives as the control disk. One, because I have a couple dozen of these already. They're tried and true. They're 7200 RPM drives, and so these are basically going to be used as the control disk and when I do the RAID experiments especially, so I can compare it against that. But I also threw a MDRAID Plus, WD20EFZX drive into the mix, as well as a Seagate Skyhawk surveillance drive, and the ST2000VX008. The reason why I chose this, I wanted to get a Seagate Iron Wolf, but at the time I purchased these drives, even on the used market, the Iron Wolf was significantly more expensive than these other drives here. So this is a 5400 RPM surveillance drive, and it is CMR though. Now for the SMR disks, we have the Seagate Barracuda Compute. Now the latest versions of Seagate Barracuda, this control disk here, Seagate Barracuda ST2000DM001, these are about 10-year-old disks. Okay, these old ones were tried and true. They've been around a while. But as the time went on, they changed the Seagate Barracuda line to your traditional consumer level disks. They call it Barracuda Compute. But this is an SMR 2 terabyte. ST2000DM008 is the model number. And then the WD20EFAX Western Digital Red. Those originally were CMR, but over the last several years they switched them over to SMR. You have to get the Red Plus or the Red Pro in order to get the CMR models now. And then also the WD Blue, the WD20EZAZ, and this one is also SMR. Now as far as the file systems that were tested and the RAID configurations, first we'll look at the file systems that were used. And first of all, we have Windows 10 using NTFS, both as an individual disk over SATA, as well as NTFS on a hardware RAID and a direct attached storage or DAS device, a QNAP TR004, which has its own onboard hardware RAID. And that RAID setup was formatted with NTFS and connected over USB 3.0. And then the rest of the tests were done over 1 gigabit Ethernet, SMB. And the file systems used were primarily over Open Media Vault, ext4 as an individual disk, ext4 over MDADM RAID 5. Those were 4 by 2 terabyte, and then ZFS 4 by 2 terabyte RAID Z1, again in Open Media Vault. And then I did use a Synology unit, the DS920 Plus, using BTRFS and SHR1. SHR1 is basically Synology's implementation of RAID 5. and then lastly UnRAID with XFS, and then I had 3 data disks and 1 parity disk. And one thing I didn't note here is I also did do a SnapRAID configuration as well using ext4, so we'll go over that. So the actual tests that were completed, just a quick summary here. I did 2 full read and write tests, as well as a rebuild of the CMR array, basically taking the ST2000DM001 disks, swapping out 1 disk with one of these remaining other 5 test disks, and recording the time that it took to rebuild that array. And then lastly, took a look at the effects of trim. And then the rebuild performance was tested on an MDADM RAID 5 in Open Media Vault, a RAID Z1 in Open Media Vault, SHR1, and a Synology DS920 Plus, and then also UnRAID with parity and SnapRAID. UnRAID with parity, I put ext4 there. I'm sorry, that should actually be XFS. That's SnapRAID using ext4. And then lastly, I did a full swap of the ST2000DM001 one at a time and a MDADM RAID 5 with the MDRAID drives, just to see switching fully from CMR all the way to SMR. And lastly, the trim effects. Basically, when I did these tests, I ran them again, and on a few different configurations here. And after I deleted the files, I ran the trim command manually. I let it idle for 4 hours before the next write test to see if trimming the disk, giving it idle time, it would actually improve performance at all. And I did that for NTFS single disk, ext4 single disk, and 3 by 2 terabyte MDADM RAID 5 and 3 by 2 terabyte ZFS Z1. As far as test equipment, I had 2 PCs. One was a Windows 10 machine, which basically ran the PowerShell script and sent data to and from over the gigabit Ethernet over SMB, and used a couple of SSDs, one to send the data from, the other one to receive the data from to, and it used basically older technology that I had laying around. So, but there's the details there. And then as far as the actual quote-unquote server PC, which ran the Linux Open Media Vault and UnRAID, used this machine right here, an Intel Core i5-3570, and the disks themselves were stored in this Sans Digital HDD Rack 5, and it had its own power supply, the FSP Group FSP 270-60LE, so it had its own power supply separate from the actual PC. And then for networking, I just used my home networking switch, which is a 48-port gigabit Ethernet TP-Link TLSG1048. I just thought I'd mention that all this testing that took place was done through a PowerShell script that I created, and it kind of grew over time. It started as just a basic file test, but now it's 750 lines of code. And the bulk of it, though, is really just doing a copy item right here, doing the file copy, and getting the file size, and then using the stopwatch command at the start and stop of each file copied, and then creating the transfer rate based on that. Okay, now before we get into the test results, let's just kind of talk about what SMR is, okay? And so to do that, we'll start with taking a look at the inside of a hard drive. And basically how hard drives work, if you don't know, is pretty basic. You've got this spinning, this motor which spins the platter or platters up to 10 these days. This one looks like it's got 3 in here, or 2 actually. Then it's got the head on the top and the bottom of the disk. The disk platter spins at a fixed RPM, 5400 RPM or 7200 RPM, or it could be anything else, but those are typical speeds. And then this head actuator arm pivots across the surface of the hard drive here, and to intercept the data that's on the tracks on this disk as it spins around. Obviously, never open up a hard drive like this unless you know that you don't need the data on it anymore. This disk just happened to be dead, so I'm using it as demonstration purposes. But if you open up a disk like this, just a disclaimer that you're probably going to lose the data on it, because even the smallest amount of dust or anything on there can ruin your drive head and your data. All right, now let's go ahead and take a look at how hard drives work and how SMR tracks are laid out and everything on a hard drive, and why it could be a concern with your data. Basically, here's kind of the hard drive that we looked at, but just wanted to point out that Obviously the disk rotates, and then you've got this read-write head here on this arm that we showed that actuates across the surface of the platter. And on a traditional hard drive, the CMR tracks are laid out like in concentric circles across the hard drive. Obviously this is exaggerated, they're going to be much smaller than this, and keep in mind that modern hard drives have capacities up to over 2 terabytes per platter, which means over a terabyte per side of the platter, which means over 1 trillion bytes of data, or 8 trillion bits of data just on one side of a hard drive. So if you take a closer look at the head here, you can imagine that this little head, this is basically a top view zoomed way in, and obviously my rough representation here, but here's the top view of it. There's your read element, there's your write element, and that's what lays your data down onto the track. And then you look at the side view here, you can see there's your read element and your write element. Nothing's here to scale, it's just my rough quick sketch of this. One thing to note is that the read element is much smaller than the write element, and SMR takes advantage of that fact, and we'll talk about that how in a second here. Okay, so here is basically the side view of a hard drive. This is the hard drive platter, or the top surface of the platter, and this is the drive head, which hovers just above the hard drive surface, and this is how it manipulates the data on the hard drive to store ones and zeros. So effectively what you have here are what are called there's magnetic grains in here. Typically it's some sort of cobalt alloy, and they're arranged by these magnetic regions, and it's given a polarity, magnetic polarity bit, basically 1 or 0 based on the polarity of the bit that's exposed at the top surface, either up or down, north, south, plus, minus, however you want to look at it. And that's controlled by the write element of the hard drive head here. And so it'll zap this to flip that polarity one way or the other, and that basically effectively stores it's basically an analog way to store binary data. Okay, and then the read head obviously just reads whatever polarity is there and then feeds that back to your hard drive and back to your system so it can reconstruct the data into usable data. Now this is called PMR, platter side view, because PMR stands for perpendicular magnetic recording, and that's typically been synonymous with what's called CMR, or conventional magnetic recording. That's because this has been used for probably over the last 20 years or so as the traditional way of manufacturing hard drives. Prior to that, there was longitudinal magnetic recording, where basically these bits were rotated 90 degrees, right? And so it had a much wider swath of data storage there. It was easier to read, and then as technology progressed, they realized they can rotate these 90 degrees, fit a lot more data on your hard drive, and go from there. Now this part of the technology is the same for CMR or SMR disk. There is no difference, okay? But where there is a difference, if you continue on, now CMR tracks are laid out on your hard drive, as we showed earlier, in concentric circles. Obviously you zoom in, they look like parallel tracks here. And as the hard drive head passes over it, you can see here that the read head and the write head have no issue. If you want to write data, it just can write it over that track, and you can read data from anywhere within that track there. SMR tracks, on the other hand, as it writes data, it overlaps the tracks, right? Well, and then after you've written data to the hard drive, well, you can always read the data later, right? Because this can basically, as long as it's positioned properly over that track, the read head can read the data off there, no problem. But if you go to write, you can see here that it overlaps those tracks, which can cause data loss. So you can already probably start to see an issue with the SMR disks here. But how do they manage this? Because you can't just go in here and overwrite this stuff. You'd have to basically remove all the data before it and rewrite over every other track again, just to write back to a section right here. Now, this is just a quick representation to show that you can fit, obviously because you overlap tracks, you can fit more SMR tracks in the same space that you can fit CMR tracks, which gives us added data density. All right, now when a computer writes data to a hard drive, it goes through your file system, right? Now, every file system has some sort of file table where it basically manages what the file name is and then location where it's stored on the disk. Okay, it's just some sector numbers. It can be, contiguous group of numbers or multiple groups of numbers depending on where it is at the disk, but it uses that to reconstruct the data back to the file. Now that's called logical block addressing, And effectively, the computer says, hey, hard drive, I need the data from these sections here, and then the hard drive itself has its own physical location for that data on the hard drive, and it feeds it back to the file system so it can reconstruct that file. Now these may match up exactly with what the LBA is. It may not, but it doesn't matter, because either way, it's a translation between the hard drive and the file system. So here's some CMR tracks, okay? And let's say we go to, we wrote the files on the disk, and these zones here represent that particular file, okay, and those locations. These are made up numbers, okay? I just put these here for arbitrary, just for demonstration purposes, so I don't try to put rhyme or reason to it. In any case, so basically you're looking at the tracks on the hard drive, and these are the files and the bits that represent that file. So let's say we wanted to delete a file. When you delete a file on a hard drive, basically all it does is it just deletes the entry in the file table. The data remains on the hard drive itself. So the hard drive is pretty dumb. It doesn't know or care. It just says, okay, the file system says I want data from this section, and the hard drive provides that data, or it says write data to the section, and so the hard drive writes the data to that section. So while the file system thinks that it's gone, the data for the file still exists on the hard drive. And that's kind of why you can recover data if you've actually deleted files, because just the pointer to that file is deleted, not the actual data. In any case, now let's say we wanted to add this new exe.zip file in that same location, general location as that file 2 was after we deleted it. File system says, hey, there's a free space there, let's throw it there. And so it does, and it can just, in CMR, it can just overwrite that. It doesn't matter if there's other data in the way, it can just zip over there and overwrite that data. Now in SMR, on the other hand, right, as it goes to write data, it overlaps the tracks and it places the files down, right? Now let's say we delete file 1.jpg, and then we want to put the exe.zip over that location like the other example, but obviously we overwrite that data. Well, what happens? Well, we are overlapping this other track, and we're going to corrupt any data that's on the other track here. So we can't do that. So how does SMR handle this? Well, basically it splits up the data into what are called SMR zones. So basically, if it wants to write a file into this position, it can basically just only have to write for these sections here and not the entire disk worth of data. So as it fills up data, right, it overlaps, and there you go. So let's say another example, we have the file 1.jpg in that location, and then we delete that file like before, but just the pointer to that file is gone. But now this data, we're going to call it dead data. It still exists on the hard drive, but as far as the file system is concerned, it's gone. Okay. Now, similar situation, we want to add the exe.zip file. The file system says, hey, there's a free position in this location here. We can fit it right in there. And then if it goes to overwrite it, again, you're going to overlap those sectors. Well, in this case, what it's going to have to do is it's going to have to go through a whole song and dance, okay? It's going to take everything from this SMR zone. It's going to read there and then write it down to a new location on your hard drive. Sometimes it puts it in what's called a CMR zone. Like there's a certain amount of CMR sections that are on a hard drive. So that way it's used as somewhat like kind of like a cache, so that it doesn't have the write performance penalty like SMR does. So, and then once it does that, it can add the new data, right, the exe.zip, and then it goes and reads the rest of the data and puts it over the rest of that section. Now, depending on the brand of hard drive, sometimes that SMR zone, it just leaves the data there, and then your hard drive just says, okay, this data now exists in this position instead of the old position. Other ones will actually read it and then recopy it back to the original position. Okay, now as a quick example, and just to show you how this can affect performance, you can probably see that already, that it could be a problem because it has to do the read, write, and possibly read, write again. Let's say this grid here represents SMR zones on your hard drive, okay? Blue are basically empty or data that can be overwritten. Gray means it has some dead data like we showed in our previous example, and then green means it's all good data, data that's alive and that the file system recognizes. Okay, so as you get a new disk, you can go ahead and just start writing to your hard drive, And as it goes along, everything's perfectly fine. But obviously, as you start adding data, you eventually want to delete data. That's what those dead data zones, gray zones, are showing. And obviously, as the disk fills up, it starts to say, hey, I need to find a spot for some of these other new files. And so then it'll start writing in those old zones. You can see there it obviously slows down the write performance there. And obviously, as your disk gets more full, eventually you'll start deleting more data because you say, hey, I'm running out of space, I need to store more data. Well, now you can see here your performance is greatly degraded because instead of just popping it in one spot, it has to go back and do the whole read, write operation again. Now this can be mitigated somewhat by something called the trim command, or also known as discard command in Linux. In the FS tab configuration when you mount your hard drives, or you can also use FS trim in Linux. Windows, you can either go into optimize, defragment and optimize disks, or you can go to command line and do a defrag drive letter /L, and it'll trim the drive if it supports trim. That's the thing, trim has to be supported by the disk, the operating system, and the file system, and then also the protocol that connects the two, so basically SATA or USB. SATA, trim is basically a SATA command, so it should not be a problem, but if you connect over USB, not all USB controllers are created equal, and it has to support what's called UASP, but that's neither here nor there. The whole point here is that when you go to delete data, right, it basically, there you've got your dead data there, and then once you issue a trim command, either automatically through the file system periodically, or you can do the manual trim, you say, okay, trim these disks, and what else it does is it flags those locations where it has dead data, so that when your computer is idle, it can go through and clean up those zones so that it can just basically write over those areas. The next time you issue a write command, it doesn't have to go through the whole read, write, swap process. And one last thing that I want to talk about is fragmentation. Now, fragmentation affects both SMR and CMR disks. It doesn't matter. Basically, what happens is you add files to your hard drive, right? And as you fill up and add files, and as your disk gets full, you eventually get to a point where you want to delete files, right? Because you want to add more data. Well, and then later you want to add a file which is much bigger. In this case, it's 1, 2, 3, 4, 5, 6, 7 blocks long. Well, you don't have 7 contiguous blocks on here, so basically what it does, it just has to fill it in locations that exist, and that when it goes to read the data then, right, obviously it's going to take longer because it has to go to multiple locations to pull that data. So obviously, typically you want it in a contiguous location like here, but when it gets fragmented, it's all over the place on the hard drive, so it's just going to affect performance that way. And I kind of took that into consideration when I set up the couple read-write tests, because I don't want fragmentation to be an issue. So, and we'll talk about that in a little bit. So here's the process for the test procedure. First, before test 1, we basically fill the array with random data, leaving about 1.2 terabyte free for the test data. This data is considered base data, and it's persistent throughout the test and it doesn't change. Then we go ahead with the test, and we start to fill the test portion with random data. This will ensure every sector has data written to it. Here's the typical distribution of the file sizes of the fill files comprised of random data. Then those files are deleted, and using a PowerShell script, the test data is written to in full and then read back with the transfer rate documented. That test data is then deleted when complete, and then the next test starts, test 2. So in test 2, the test area is filled with 10 megabyte files of random data. Then every other 10 megabyte file is deleted. 1 gigabyte size files of random data are then written to and read from the array, and transfer rates are documented. When it's complete, all the test files are deleted. Basically what this test does is it ensures that there are plenty of gaps in the SMR zones to see how performance is affected. After test 2 is complete, we go into test 3, and the next test disk is installed. the array is rebuilt and the time to completion is documented. And then we start back at test 1 until all the disks have been used. For SnapRAID, the procedure is a little bit different because it runs a little bit differently than traditional RAID configurations. So first we'll fill 2 data disks to about 90% capacity. Then we'll fill data 3, which is the test disk, with 600 gigabytes of random files. Then we will generate parity on the parity disk. Now we will swap out the data 3 disk with a new test disk. Then we'll restore data from parity and document the time to completion. And then the read-write tests will be run, test 1 and 2 will be run on that data disk. After that's complete, it will delete all data. Then we will rebuild from parity and then document the time to complete. Okay, now here we go with the test results. Now before we actually look at the test results, let's go ahead and take a look at the baseline for all these disks. Basically what I did is used hard disk Sentinel and did a full disk wipe. Basically it starts at sector 0 and writes on the disk all zeros all the way down until it gets to the last sector on the disk, or last bit on the disk. And this is a typical hard drive curve just because you have more data, because data is populated at the same density across the disk. So further out from the disk, it's going to have a faster angular velocity. And so it's going to be able to read more data at the outer edge of the disk versus the inside of the disk. So the yellow and the green that you see here are the Seagate Barracuda and the Seagate Barracuda Compute. And those, the green one is the CMR Control one, the yellow one is the SMR Barracuda Compute. These are 7,200 RPM drives. That's why their performance curves are a little bit higher. And then you've got the red line, which is the WD Red Plus CMR, pink line WD Red SMR, light blue line, which is the WD Blue SMR, and then lastly we've got the Seagate Skyhawk purple line here, which is CMR. And then I also did the same thing with the reads, and it pretty much is identical to the write performance. Next up are the SSDs. Now the SSDs were just used to read from in order to send data over to the test array on the either Open Media Vault or on the SATA drive in Windows, or to the USB attached DAS QNAP device, etc. So that was the Mushkin reactor here, which is the pink line, and so it had a steady read performance of about 475 megabytes per second. And then the Crucial MX500, that was used to, when you did the read test from the test array, so it was actually writing to the SSD and pull the data off and store it on the SSD. That read and write performance was right around 350 megabytes per second. So there was no, just to show that there's no performance hindrance from the SSD during the disk testing. Okay, so now on to the actual test results. Now I'm just going to go through this one slide here, kind of explain it a little bit in detail so see what you're looking at. Then I'm just going to kind of plow through the other graphs, and you can take a look at those at your leisure. But the first set of test results are all going to be the write performance. Then I'm going to do the read performance of those mixed file writes. After it wrote all those files to the disk, it read them all back. And and this red dotted line here basically means that these are the SMR disks, just to kind of highlight which ones are the SMR, and then these are the CMR disks down here. And the first test is NTFS single disk over SATA, and these are the results. And obviously, higher is better as far as the transfer speed. And since this is over SATA, it could go up to, obviously 600 megabytes per second, but no hard drive is capable of that. And these 1 megabyte, yellow is the 1 megabyte file size, transfer blue is 100 megabyte, orange is 1 gigabyte, and green is 10 gigabyte. Now, obviously, this 1 megabyte performance seems a little high. It's probably because of caching reasons, and they're small files. So, okay, next is the QNAP TR004, right, using NTFS over using a hardware RAID 5 over USB. The next is a Synology DS920 Plus, SHR using BTRFS, again over 1 gigabit Ethernet. And then we move on to Open Media Vault ext4 file system on a single disk. And then Open Media Vault ext4 over a MDADM or MDRAID RAID 5, and file transfers over 1 gigabit Ethernet. And then we have Open Media Vault ZFS RAID Z1. Again, file transfers over 1 gigabit Ethernet SMB. And then UnRAID as a test disk, as a data disk. And then the test disk is now a parity disk in this graph. And then here we have the read performance results, basically the same test we just looked at, but this time it's the read, so basically reading data off the hard drive array or single disks from the test server. QNAP TR004 DAS unit, formatted NTFS with the hardware RAID 5 over USB 3. Synology DS920 Plus, SHR with BTRFS file system, again transferred over 1 gigabit Ethernet. Open Media Vault ext4 single disk. And then Open Media Vault ext4 MDRAID or MDADM RAID, however you want to call it, RAID 5 over 1 gigabit Ethernet. And Open Media Vault ZFS RAID Z1 over 1 gigabit Ethernet. Now UnRAID test disk is parity. Okay, now we're on to the test 2, basically where we write 10 megabyte files through the rest of the disk, delete every other 10 megabyte file, and then write 1 gigabyte files, 600 of those, and then we read those back as well and record the transfer rates of both. Now here what we have is both the write and read performance in one graph, because we don't have all the multiple file sizes to deal with. So the red represents the write performance, the blue represents the read performance. And again, the red dashed line represents, just to highlight the SMR disks on this chart. So the first one is NTFS single disk over SATA. Next one is the QNAP TR004 DAS unit, formatted NTFS using their hardware RAID 5 over USB 3. Then we have Synology DS920 Plus, formatted BTRFS with a SHR1 RAID configuration over 1 gigabit Ethernet. Next we have Open Media Vault ext4 single disk over 1 gigabit Ethernet. And we have Open Media Vault ext4 RAID 5 MDADM RAID over 1 gigabit Ethernet. Then we have Open Media Vault ZFS RAID Z1 over gigabit Ethernet. Then UnRAID XFS with parity over gigabit Ethernet with turbo write enabled. Next we have test 3, which represents the rebuild times. So the tests that we're going to look at are basically, we start with the 4 ST2000DM001 disks, the test disks or the control disks, in a single parity RAID configuration. Then we replace one of those disks with one of the test disks, 2 of the CMR in each of the 3 SMR, and each time we go to rebuild that array, we record that time. And then we will also do a test row where we start with 4 ST2000DM001 hard drives, and then incrementally replace each of those with a WD-20 EFAX SMR drive. So basically start with 4 CMR drives and then pull an CMR drive, add an SMR drive, pull another CMR drive, add another SMR drive, and do that until all 4 are replaced. And lastly, we're going to look at the comparison of different RAID controllers. The LSI 9211 8i, which is basically a SAS to SATA adapter plugged in PCIe configured to IT mode. So basically it's a pass-through. And then the onboard Intel 877 Express SATA, and then the Marvell 9215 SATA PCIe add-in board. Again, we have the SMR disks highlighted by the dotted red lines. And you'll see at the top I also highlighted the SMR disks with the red graph. That's just to differentiate them from the CMR at the bottom in the blue. And obviously time in minutes, so lower is better. Quicker time is better, right? And the first one is the QNAP TR004 with the hardware RAID. Next is the Synology DS920 Plus, an SHR1 one-disk parity RAID. Next is the Open Media Vault MDADM RAID 5. And then we have the Open Media Vault with ZFS doing a RAID Z1 rebuild. Clearly here the Barracuda Compute ST2000DM008 had some significant performance impact problems. And then next we have SnapRAID EXT4 formatted. Then we have 3 data disks and then 1 parity drive. And as explained previously, is the light blue indicates the initial write of data to that disk from parity, and then the dark blue represents after filling and deleting data on that disk, then deleting everything on that disk again, and going ahead and rebuilding that disk again from parity. So the sync before we tested, and then a full sync of the data after the test. Okay, now this is the parity disk rebuild times for SnapRAID, a little bit different than the data disk we just looked at. And so kind of explained here, the light blue represents basically building a new parity disk with your test disk, right? So it's going to have as much data on it as your largest data drive. So since 2 of the disks were filled with 1900 gigabytes of data, your parity drive is going to be at least that size as well. And then, so that's basically the initial sync. Now what this other dark blue line represents is filling that third disk all the way to the top, syncing, deleting over 500 gigabytes of data, syncing again with parity, and then filling up another 500 gigabytes of data. And so that last sync is what this value represents. It's going to be a lot shorter because it's only syncing the changes that were made to the files, not the whole array. And then UnRAID, here in this graph we have light blue is data, dark blue is parity. So that's test disk is data disk and test disk is parity disk. And then lastly, we have where we swap the CMR disks for the SMR disks and then the SMR disks for the CMR disks. So basically we start with 4 ST2000DM001 CMR disks here, and then we pull one of the CMR disks, put in a SMR WD-20 EFAX WD RAID drive, rebuild, that's that time, and then we pull the next CMR disk, put in a new SMR disk, rebuild, and then that's that time, etc., so on and so forth. Then after that's done, I do the opposite. I go from start with 4 SMR disks and then replace them with CMR disks. And these are the resultant times after swapping each of those disks. And then this one is specifically for the QNAP TR004 hardware RAID. Next one is for the Synology DS920 Plus with an SHR1 single disk parity. And then the next one is Open Media Vault MDADM RAID 5. And then lastly, we have the different controllers. I ran these in Open Media Vault, MDADM RAID 5, and used the LSI 9211-8i, the onboard Intel SATA controller, and then the add-in board Marvell controller. And you can see here that the LSI performed the best in general, and the onboard SATA controller actually didn't do too badly. And then lastly, the Marvell add-in board obviously lagged behind the other devices pretty significantly. So it just goes to show you that the controller that you use can affect performance as well. And then did the same thing with RAID Z1. And then lastly, we have the trim. And this is where basically I ran the write tests. And whenever I did the mass deletion, after I wrote all the data, deleted the data, then went to go write the next data. After I deleted all the data, I initiated a manual trim, either an FS trim in Linux or a trim command in Windows, and then give it 4 hours of idle time before it continued with the next write process. So that should have given the trim command and the hard drive enough time to clean up whatever SMR issues there were out there and see if it improved performance at all. So what you're looking at here is a separation of the disks. Here we have WD Red without trim, and then with trim. Here we have WD Blue without trim, WD Blue with trim, and Seagate Barracuda Compute without trim, and Barracuda Compute with trim. This particular test result is for NTFS single disks over SATA, because it was a local test, and then the write performance. And obviously higher is better, because it's higher performance, it's megabytes per second. Then here's the actual read performance on NTFS single disk over SATA. And then the 1 gigabyte, this is basically test 2 with the writing the 1 gigabyte files after 10 megabyte fill and delete every other 10 megabyte file. In this case, the red is the write performance and the blue is the read performance. So you can see here trim had a significant impact on the WD Red and the WD Blue, but almost nothing on the Barracuda. Because initially it was 37 megabytes per second to write. After it was able to trim, wait 4 hours, and do the same test again, it improved up to 85 megabytes per second in this case. And Blue went from 36 to 130. Now this is the Open Media Vault ext4 single disk test. Write performance. And then we have the read performance. Then the 1 gigabyte file, again, write and read here. So WD Red improved slightly, WD Blue improved quite a bit more, and the Seagate Barracuda would not trim within Open Media Vault. For some reason, it just would not recognize it as trim, even though it is supposed to be able to trim, and it could trim within Windows just fine, but it would not, FS trim would not work with this. And then the 4-disk MDADM RAID 5 over Gigabit Ethernet. This time the disks initiated or were mounted with the discard command, and then also an FS trim was manually run at the end of each delete cycle with a 4-hour idle time. Now you'll see here that this has 3 WD Red disks, and here WD Red disks without trim and with trim. The reason why there's only 3 here, not 4 like the other tests, is because on the WD Red, for some reason, 3 of my 4 disks are the same, I guess, version or model. Like the model at the end is a little different on one of the other disks. And even though that one had trim support in Windows, like that Seagate, it did not support trim in Linux. So I just decided to go with a 3-disk RAID 5 array for these results rather than a 4-disk. So that way everything could be trimmed. And then the read performance with those same disks. Then the 1 gigabyte file transfer after the 10 megabyte fill and delete. See, in this case, there was no improvement. And then we go into ZFS, and here's the RAID performance. With and without trim, really no difference. And then here we have the read performance. For some reason, the X3 read performance was on the 1 megabyte file sizes were pretty slow. Trim helped a little bit, but not a whole lot. And then the 1 gigabyte files after 10 megabyte fill and delete. In this case, you can see that the trim actually helped significantly. It improved it by 30 megabytes per second. And finally, here we have a test summary. And basically what I tried to do is consolidate all this into a few succinct charts so that kind of get a feel for what the performance difference is between these disks. And so what we see here is RAID performance percent slower than ST2000DM001. That is the control disk, the Seagate Barracuda 7200 RPM CMR hard drive. And then what we have here then over the left vertical axis here is the percentage, okay, in relation to that disk. And percent slower, basically, than that disk. Now keep in mind that the ST2000DM001 is a 7200 RPM CMR disk. All the other disks are 5400 RPM with the exception of the Seagate Barracuda Compute SMR disk, ST2000DM008. So basically anything under 20% should be considered within normal parameters, okay? Just because of that spindle speed difference, you should expect a little bit slower performance there. And then we have this broken down by hard drive. CMR WD Red Plus is pink, CMR Seagate Skyhawk is white, green SMR Seagate Barracuda, light blue is SMR WD Blue, and red is SMR WD Red. And you have each of the different tests here: BTRFS as SHR1, MDADM RAID 5, EXT4, ZFS RAID Z1, QNAP TR004 DAS unit connected over USB and Windows NTFS, and then Open Media Vault, EXT4 single disk, UnRAID XFS single disk, and NTFS single disk over SATA. Now, what we have here is the 1 gigabyte alt, which basically means test 2. So that's where all the 10 megabyte files were added to the disk, every other one deleted, and the 1 gigabyte files written. And then these other values here represent test 1, basically where the disk was filled with the random data, all that data was deleted, and then went back and wrote these different size files, hundreds, thousands of those to the disk, 620 gigabytes in total. And so you can kind of see here now, the light green, the Seagate Barracuda kind of stands out here, and in general with its performance not so great. WD Red even stands out in the ZFS and the Open Media Vault EXT4 single disk test in the test 2 scenario here. But otherwise the other disks seem to do fairly well. Now here is the read performance with respect to that Seagate Barracuda CMR test disk or control disk. And you can see here it generally read performance was affected a little bit, but not by a whole lot. And the ZFS seemed to be the most problematic. Then the 1 megabyte files in a couple of these tests seem to throw that off by a little bit. So the smaller files can tend to be an issue because of caching. And now here's the summary for the rebuild time. Now this is the percent longer than it took than the ST2000DM001 to rebuild a single disk in a 4-disk array. And so we have here MDADM RAID 5, ZFS RAID Z1, Synology SHR1, the QNAP TR004 RAID 5, hardware RAID 5, and UnRAID XFS, and then the SnapRAID EXT4. And this is time in minutes over here on the left. Sorry, that should actually be percentage. I apologize. That is percentage more than what it took to complete ST2000DM001 to rebuild. So clearly everything here is pretty much within normal, reasonable amount of time, less than 20% for the most part. I have a couple flyers here with this WD Red and then the Seagate Barracuda and the ZFS Z1 array, and then also SnapRAID EXT4. And now we're looking at trim percent improvement. In this case, we are comparing this with respect to itself, basically without trimming, and then once we trimmed the system, then we did the test again, and these are the results. The difference between trim versus no trim. So on the left here, vertical, we have a percent improvement. So for example, this over on the right here, you have the WD Blue, a single WD Blue disk in Windows 10, NTFS over SATA. These numbers here represent the 10 gigabyte, 1 gigabyte, 100 megabyte, 1 megabyte file transfer on test 1. And then the 1 gigabyte alt represents the test 2 file transfer percentage improvement. So you can see here on test 1, there really was not a whole lot of improvement in general with the write performance after trimming. So basically, once the disk was filled and then the files deleted before starting the test, the disk was trimmed, allowed to let idle for 4 hours, and then the write test commenced. And we can see though on test 2, the improvement was pretty substantial. This is where the 10 megabyte files, every other 10 megabyte file were deleted, and then 1 gigabyte files were written. So in most of these cases, ZFS Z1, OMV XT4, NTFS SATA with WD Red and WD Blue SATA, and then also WD Blue Open Media Vault ext4 single disk. There's significant improvements. So basically, this one is 2.5 times or 261% faster in write performance than without trim. And then as far as the read performance after trim, this one's a little bit interesting because usually you wouldn't expect read performance to change a whole lot, but it seems like this 1 megabyte file size is a little bit problematic as well, probably because it is a small file size. There's some caching going on there as well. And but again, the WD Blue in Windows 10 under NTFS SATA, we did have some significant improvement, I would say, 15 to 19% improvement in read performance after data had been, or the disk had been trimmed. And as much as 48% of the 1 megabyte file, and then the test 2 data, 32% improvement there. And then the Open Media Vault ext4 single disk test, you had a 16% improvement on the test 2, and then everything else was pretty much on par. The weird thing is this WD Red SATA disk actually had a negative performance improvement or a performance reduction after the disk was trimmed, which is kind of odd, but it is what it is. Okay, and here's a summary from all the testing, and I'll go through the different scenarios that we went through. Basically, write performance of the SMR hard drives in general was better than anticipated, especially in RAID scenarios. The Seagate Barracuda Compute ST2000DM008 SMR disk had the worst performance overall by a small margin, although it was significantly worse with the test 2 scenario, even after trim and giving it some idle time. So trim seemed to have minimal effect on this disk. Surprisingly, the WD Blue WD20EZAZ SMR drive performed as good as, if not better than, the WD Red SMR disk and the WD Red Plus CMR disk, which were coined as NAS drives by Western Digital. And in a few scenarios, though, the SMR disks performed 30 to 50% worse than their CMR counterparts with the first test, but it was still at a reasonable 70 to 80 megabytes per second versus 110 megabytes per second of the CMR drives. And although test 2 results were considerably worse, running at only about 20 to 50 megabyte per second write performance in ext4 and NTFS tests compared with the CMR disks above 100 megabytes per second. But after trimming it and giving it some idle time, the performance was restored. Regarding read performance, it was generally not affected. However, after the trim test, the NTFS single disk results for the WD Blue SMR disk did improve by an appreciable 15 to 20%. Now into the SMR RAID rebuild testing. Now, performance was generally comparable to the CMR disks, with the exception of the Seagate Barracuda Compute SMR drive and the ZFS test, which took over 500 minutes versus the 180 to 230 minutes of the other disks. But the other SMR disks actually fared pretty similarly to the CMR disks. Now, in SnapRAID, using ext4, the Seagate Barracuda and the WD Red, both SMR disks, they both faltered a bit with the post-test sync running about 160 minutes and 123 minutes respectively, compared with about 90 minutes for the CMR disks. And then rebuilding a 4x ST2000DM001 CMR array and then replacing incrementally with a WD20 EFAX WD RAID SMR disk one at a time, and then doing the reverse, going from the SMR disks back to the CMR disks. There was really no significant impact on the time to rebuild with those disks. And then did a limited controller rebuild comparison, and the LSI 9211 8i, which was the primary controller used for all this testing, and then also compared that with the Intel H77 SATA controller that was on board. And then those two actually had rebuild times within 10% of each other, so it didn't seem to affect it a whole lot either way. But I did also try a Marvell 9215 add-in board, SATA add-in board, and it took about 25% longer to rebuild than the other two cards did. Now, during the trim test, trim did not seem to have much of an effect with test 1 scenarios, except for NTFS single disk with 18 to 30% improvement. And part of that, I believe, is because basically we wrote a bunch of data, we deleted a bunch of data, and I think that there was some logic possibly in the hard drives themselves that said, okay, it realized that there was deleted data, bulk deleted data, and it could just overwrite all those SMR zones, no problem. But trim did have a significant impact in restoring performance in all cases for the test 2, which was basically writing all the 10 megabyte files, deleting every other 10 megabyte file, basically a controlled fragmentation situation there, and then writing 1 gigabyte files on top of that. And that improved performance by as much as 50% with RAID Z1, and up to 261% improvement, 2.6 times improvement with NTFS single disk. So trim definitely did help. And then lastly, I want to talk about the disks themselves. I did RMA a few of these disks. Now the ST2000DM008, the the Seagate Barracuda Compute Drive SMR disk, had to be RMA'd at one point during testing because it became non-responsive. And then 3 of the 4 actually had 5 WD20 EFAX SMR hard drives, and 3 of those had to be RMA'd. One of them was kind of questionable whether it really needed to be, but one was for bad sectors. It clearly had bad sectors. The other one ended up becoming non-responsive like the Barracuda Compute did. The last one was just throwing some write errors with ZFS. The other WD RAID disks were not. And although that RAID disk was actually working fine on the other arrays, but I decided to RMA it anyways. I didn't question it, and I got it. All those had a turnaround of less than 2 weeks, and all the replacement hard drives actually fared well with the remainder of the tests. And I'd also like to note that I personally don't encourage the use of SMR disks in any RAID configurations or in general, despite them typically priced less than CMR disks. The biggest appeal for SMR is lower cost, although in reality the cost difference usually isn't substantial enough to justify their performance concerns. Traditional CMR disks designed for the task at hand are the best options to consider, so buy a NAS or enterprise disk. Typically the cost difference between a SMR and CMR disk, in my opinion, isn't usually that substantial that it justifies needing to buy the SMR over the CMR, especially in a RAID array configuration. For a single disk in Windows or Linux, it's probably perfectly fine. Trim seems to work fine there. Just give it plenty of idle time. And lastly, back up your data. In any case, hope you learned something today. Hope this was helpful. And until next time, talk to you later.